So, hello, ladies and gentlemen. I hope you can hear me and can see my slides. We have had in the last lecture, when I remember right, this example, the huge task with the calculation of the values, and we have used the line approximation. And now I would like to show you an example which is a little bit different. And we have here a flow. We have a flow, we have a basin, and we measure the delta of the pressure before and behind of the basin. That is a very often used measurement system for flow measurement in the industry. And the important thing is that we have a non-linear function. You see here the formula. The flow is alpha, that's a constant flow coefficient. Alpha is determined practically. That is a little bit depending from the shape of the basin. Is this here sharp or is this not sharp? How looks this side of the basin? And therefore, this is, let me say, a correction function. It is practically determined. And then we have A0, that is this area. And the most important thing, let me say, we have here the density of the material. In our case, it is water. And so that you have here the density of the medium, 1 gram per cubic centimeter. That means it is water. And the most important thing is the delta of the pressure, because when you have a higher flow, then you have an increase of the delta of the pressure. And that is what you would like to measure. But you see, here is a root in. That means the dependency is non-linear. And in this case, when you know this non-linearity, like in this formula, then it is often very comfortable when you correct at first the non-linearity. Of course, when you have a non-linearity, let me switch to my drawing board. When you, oh, little moment, I must connect the board. Now I have the board. When you have a known non-linearity, let me say it's going so. Of course, you can use the line approximation with many points, so that you can correct also the non-linearity. But in many cases, it is easier when you know the mathematical function, then you take at first a mathematical non-linearization. You can, when you have the root as a function, you can power it by 2. If you have a powered by 2 function, you can take the root. So that you have, when you do this, a nearly linearity. And then you can correct with 2 points, or if you have a rest of non-linearity inside, you can take a third point, so that you make the line approximation with less points. And that means less points means you need not so much calibration standards. And especially when you work in the field of, let me say, analytics, where you have an, let me say, a particle size analysis also, or gas analysis, where the standard what you give on is lost after the calibration. You put a gas in and clean it in the end from this gas, then you lost your standard. That can be also that it is a question of money, because every standard is expensive, and especially standards which you lost after the calibration, then it is a question of the cost. And that is what we would like, what I would like to show you. Here you have all the parameters which you need, and you see here the flow 0 leads to the ADC number 32, and the flow of 1 cubic meter leads to the ADC number, this one. You see that is a little bit below 4096. That means it is a 12-bit ADC. Yeah, here is it also written. And from the pressure, that means the electronic, from the pressure to the voltage and to the ADC number. That means the whole electronic is linear, but the delta pressure is non-linear connected to the volumina stream. Therefore, you have also this non-linearity in your system. And these are very typical values. You are not with the highest number, you are not absolutely in the end of the range. That is normality. And the ADC number 32 at 0 is also understandable, because I can show you that in the drawing. When you have a noise around 0, let me say that's the noise around 0, then you have minus and you have plus. And when you give this on a ADC, then is all what is below is 0. Yeah, that's the analog side, and that is the digital side. Here you have the digital connections. Here you have the analog connections. Let me say from 0 to 5 volt. Then is everything what is below 0 is 0. And the mean over the positive peaks from the noise is then the systematic error. And this is in this case 32, I think. Yes, this is in this case 32. Therefore, this is absolutely a practical case, so that we can calculate with this. And the task are now write down the software for the PC with which can be calculated the measurement results for the flow from 0 to 1 cubic meter per hour. And you should test this also in the middle for 0.5, because you have the nonlinearity, and this must also be corrected. And I show you now the ways. At first, we make an analysis of the whole measurement system. And you see here, I have 3 points, 0, 0.5, and 1 cubic meter. And then we have this formula that is the same like this, but all the constant parameters like alpha, A0, and the density I have put in a constant here. This is a constant where all these parameters are in, and then have you this function. You go in with the volumina stream here, and you calculate the pressure. And you see here the values for the pressure. And here you can already see that this is nonlinear. You see here the power by 2 function. Otherwise, when it would be linear, that should be in the middle between 0 and this upper value. But it isn't, caused by this nonlinearity in the dependence from the pressure to the flow. And then you go into the electronic with the amplification, with the ADC number, and we said this is linear. The electronic is linear. You can, for practical applications, you can say in the absolutely most cases, it is true that the electronic is linear. And you have an M, you go with the delta pressure in, you have an N, because these are the ADC numbers. These are not the measurement results. These are the ADC numbers. And now we have to calculate all these constants. What are the constants? The constants are N and M, and we have here K. And this is a formula, you see, the formula, and I have changed this a little bit so that you have in the end this one, and you can calculate K and have the number 141 point and so on. And then can you calculate the M and the N, and you see here the M is 7.8 multiplied with 10 powered by 7, and N is 32. And that's also clear because we said as 0 it is 32, but you can also calculate it with the formula. And when you have all these values, then can you look for your system? This is that what we have seen just. And now you go with the ADC number in your computer, and you have to go this upper way back from the right side to the left side. That means you go with the ADC number in here, with the ADC number, you go into the computer, and you have to calculate from the ADC number the delta of the pressure. ADC number, and you go and calculate the delta of the pressure. This is the same formula, only that you calculate now the delta of the pressure from the ADC number and not the ADC number from the delta of the pressure. Then have you the delta of the pressure, and then you do exactly the same with this formula. You calculate the volumina stream with K and the delta of the pressure, and then have you the volumina stream. And when you put all your numbers in, then you come to a very short program. You read in the ADC number, oh, I have forgotten to translate it, that's a German word for number. You read in the ADC number, and you can calculate with this simple formula your volumina stream. And then can you print it, for example. That is a very easy way, but you must be sure that the nonlinearities are only from the mathematical background of the task. you should not have additional nonlinearities. It must work, the whole system must work exactly according to the theory. And that is in the most cases not so. In the most cases, you have additional to the theory, you have non-linearities from the system. So that we look for a second way. We look for a second way that we say at first, we read the ADC number in. We set the 0 point to 0. That was the n. We take now the root of the ADC. That means the root makes the linearization from the nonlinearity. But then we get completely new values for Km and Kn. Kn is 0 because we have set it on 0 at this point, and Km we have to calculate now. That means delta y, and delta y uncorrected, is now from 0 to the root of the ADC number, and the ADC number is the ADC number minus 32, and then we take the root. Therefore, this 3930, you see here, the ADC number was 3962 minus 32 is 3930. And the root, because we have taken here the root, this number is a new value for y uncorrected. And this delta divided by this delta is m, and then we calculate the Km as 1 divided by m, and you have a new value for Km. Kn is 0, and you have here this point. This formula, sorry. The advantage of this way is that you make at first a linearization. And if you measure then, if you calculate, for example, at the middle at 0.5, and you calculate, and it is not exactly linear, you see it when you have, let me show it here and make a new one. When you have it here, bigger, when you take the root and it was powered by 2, for example, then have your linearity and you can work with 2 points. In many cases, it works also with the 2 points. But when you have an additional nonlinearity, that it is not so exactly linear, then can you say, I take 1 or 2 additional points, but it saves also calibration points. That is the aim, to save calibration points. And so you can, after this line 0, you can make a line approximation that you divide this range into 1 or 2 steps and can make additional line approximation, but with less calibration points. This way is the most used way when you have a strong nonlinear function. Yes. Have you questions to this point? No questions? Then I have here the exercises, but I have uploaded this example. I think I have uploaded this example. That is another example, also with a nonlinear function. This is in English, and there is also a Russian version. In the second part of the PDF, you have a Russian version. You can read this example as an additional task. It's a question from the field of particle measurement, and also in particle measurement we have some cases where you have very strong non-linearities, and you can read this. And then we have a book, but that is in German, and there is also an example in we have it in the library, but that is only in German. Therefore, this upper is, I think that's better for you. After the lecture, I will have a look whether I have uploaded this example, but I think I have it. So please, if you have questions, ask every time immediately. I let switch on all your microphones so that you can every time ask when something is not clear. So we have two words what I would like to explain. We have the range and the precision. And there are definitions, and the measurement range of a measurement system is a range in which the input value can change without exceeding the given maximum error. That means the range is every time defined by the error. And important is that the displaying range can be bigger than the measurement range. Let me show that again in the drawing. In the past, we have had measurement devices with an arrow, and you have had the pin here, and it was clear when the arrow is on the pin, it can also be bigger. When you have here 100 volt and you have seen the arrow was on the pin, then can it also be more than 100 volt. It was clear that you are then out of the range. Today, we have normally digital instruments, and when you have 3 digits, then you can have the range on 100. That would be that. But the device can show until 999. And therefore, it is very important to know until which point is the end of the range, at which point is the end of the range. Because when the device is showing 120, it can also be 130 or 110, because outside of the end of the range is the given error not more valid anymore. The error the given error is only valid until the end of the range. Many devices works in this kind, but we have also devices, especially cheaper devices, where we say, or where the people say, the manufacturers say, maybe that are not so experienced people who work with cheap devices. They work then until 100, and then comes overflow or error or something that they not show values out of the range. But especially more expensive devices are working out of the range, because the manufacturers say, when you buy such an expensive device, you know what you do. And when the device shows 101 or 102, you can say it is the error is not much bigger as at 100, but there is the error not valid anymore. That is important. That is range, the definition of the range. And a second point is the precision. The resolution is the smallest unit of change of the input value that can be detected with the measurement device. The smallest change of the input value, that is the resolution. But the resolution is different from the word precision. For example, when you have a normal linear, then you say there is a division of 1 millimeter on, and you say the error can be plus minus 1 millimeter. That is a resolution. The resolution is 1 millimeter, but the error can be much more bigger. When you have, for example, I go again in this one, when you have a linear and you have here the millimeter resolution, then you start with 1, 2, 3. I have not count now the lines. 4. Then have you a resolution from 1 millimeter. But when you cut, for example, your linear at this point, you would have an error from 2 centimeter. That's the error. The resolution is still 1 millimeter. That means the error can be much more bigger as a resolution, but the error can not be smaller as a resolution. That is very important to know. And that's also this, what I have written here. The word precision is used very differently. Important is that the precision is completely different from the resolution. The maximum error of a system can never be smaller than the resolution, but it can be much more bigger. Yes, this was the example with the cutted linear. Therefore, instead of using the term precision, you should better use the terms in connection of the error. That is more concrete when you speak from the error. But otherwise, many people use also the word precision, but you should know what is behind this, this word, behind this expression. Yeah, have you questions? No. Then we come to another point, which is very important in especially also quality calculations of the quality of measurement values, which are determined from different measurements. It means will be calculated a measurement result from several measurements, and have the measurements errors, will have the result also an error. Shortly, that means when you calculate an area, you have two length measurements. A multiplied with B is the area. And A has an error, B has an error. And the question is, what is the error of the resulting result of the area in this case? And I think it is clear that the errors of the single measurements are important, but also how the measurements are connected. I go again here. When you have A is the length A multiplied with B, it is clear when you have here the biggest and here the biggest, you can calculate the biggest of A. But what is when you have other connections? When you have A powered by B plus C is something. Then is a question, what is that? Then is a question, you have the feeling that an error from B must have a much more influence as the error of C, because that is only added. The error of C has a not so big influence. And the laws of the calculation of the error propagation allowed to calculate this delta of the result, including the different influence according to the mathematical connection of the single measurement value. That is important, that also the mathematical construction has an influence to the calculation. And this is founded by Gauss. Gauss was a German mathematician many hundred years ago in the Middle Age, and he has found these laws of error propagation. And the main formula is the propagation of the standard deviation. The standard deviation, that means that you have to have for every single value a standard deviation. And you see here, this is a formula, and you have to make the first derivation of the formula, but the first derivation to each value which is included in this formula, and then multiplied with the standard deviation powered by 2, you add all the single values and you take the root. I will show you an example, then is it, I think, much more clear. I must have a look. Yeah. I must have a look. Have I the... No, I show you at first the single values. That is a propagation of the standard deviation, and this has a concrete mathematical basis. With this standard deviation, you can do everything what you can do with every standard deviation. The double, for the single standard deviation, you have 68.3% of the possibility that the values are in this range, and you can multiply the standard deviation by 2, then have you 95% of the values are in this range, because this formula is based on a mathematical background. This is exactly. But the problem is that in many cases, we have no standard deviation. When you, for example, calculate the volumina of an body, then have you 3 length measurements, and you measure the length, let me say with a lineal, then have you as a error plus minus a half of the resolution, plus minus a half of 1 millimeter in this case. And this is not a standard deviation. This is an error determination of another kind. And therefore, that we also can use this measurement errors from another definition, not from the standard deviation. We use the same formula, and we put here, instead of the standard deviation, we put the error in what we have determined in another kind. And so we have here, instead of the standard deviation, we have another kind of error that can also be an error class. And because this is not a standard deviation, we can also not call the result as a standard deviation. We call it as an average expected error. That's the average expected error. But you see, the formula is exactly the same. The only one's different is we have not a standard deviation for the single values, and therefore we can also not calculate the standard deviation. This average expected error is mathematically not exactly, because the true formula is working for the standard deviation, the propagation of the standard deviation. And this formula use the same formula, but we put other errors in to calculate the resulting error, and we call it an average expected error. But it is used very often in the industry because in many cases you have not a standard deviation. And the influence of the mathematical connection is also here in this formula in the same way as from the propagation of the standard deviation. When you have a value powered by 2, then have you here in this formula also a bigger influence for this powered by 2 standard deviation, powered by 2 error. So that would be the average expected error. And we have a third point, that is the maximum expected error. The maximum expected error calculate the absolutely worst case. And you see, you have not the powered by 2 and you have not the root. You add all maximum values. I will explain this. You have, for example, I make it new, then is it clean? when you have a normal distribution for one single value and the other single value has also a normal distribution, then can it be that you have a single value on this side, on the bigger value, a plus error, and you have here a minus error? That means they eliminate each other. And so have Gauss found, the mathematician has found, that this is according to the sentence of Pythagoras. You have here A, you have B, you have C. And this is shorter than this and this because you have these eliminations. But when you would like to calculate the theoretical maximum of error, you say you have here the biggest and you have here the biggest. At the same time, the biggest error from both input values. And then have you not this shortens, you have this A here. You take the absolute values and you calculate this bigger error, but it is very rare because you must have the biggest or the smallest error on both sides, the smallest error at the same time. And when you have more input values, then it is more and more rare that you have for all at the same time the smallest or the biggest error. But it is theoretically the biggest error what you can have. And especially when you have security questions, calculations of where the security of a system is depending, then are these important calculations that you calculate the most possible, the biggest possible error, also when the possibility is very low that you can have this error. But when you set up a device where pressure is in and you calculate and you have to measure, let me say, the temperature, you have to measure the thickness of the wall of this body where you have the pressure in, then you say when all the values have this stupidest error in the wrong direction, then it should not come to an explosion. Then you use this formula where you calculate this biggest error, what is possible, the maximum expected error. So, and when I look for the three formulas, then we can say the propagation of the standard deviation is the only ones what is absolutely exactly. That is a mathematical background, and you can use it, especially for scientific questions. You can use this very, very good. You get the real standard deviation for the result, what you calculate, but it is very extensive because you need for every measurement result a standard deviation. So, and then we have the second, the average expected error. This is mathematically not accurate. We use the same formula like the propagation of the standard deviation, but we put errors in which come from other sources. A half of the resolution, plus minus a half of the resolution, or an error class from electrical devices. We have, in most cases, only an error class, not a standard deviation. And we put this error from other sources in the same formula. but therefore we get a result what is very good to use, because the mathematically connection between the input values, the measurement values, are also calculated, and value which has a big influence has then also a big influence to the result value, and so on. That is mathematically not accurate, but it is very good to use, and therefore in the industry it is used, yeah, let me say, I think it is the most used way, also when it is not absolutely mathematically correct. In scientific fields, you use, if possible, every time the standard deviation. So, and then we have the maximum possible resulting error. His appearance is not improbably, but it is really used for worst case scenarios. And when you have so more input values you have, rare would be the error, the possibility that all the errors have at the same time the biggest value from all input measurement values. But theoretically, it would be the worst case. And when you have security calculations, then you should use this possibility for the maximum resulting error. So, and that therefore that it will be a little bit clearer, I would like to show you an example. We have the calculation from a volume from 3 length measurements. This is very easy because A multiplied with B multiplied with C is the volumina. And in this case, we have the length A plus minus a delta A. A delta means we will calculate not with the standard deviation, because the length measurement, in the most cases for the length measurement, you have only a delta and not the standard deviation. When that would be a standard deviation, would be the calculation exactly the same. The calculation would be exactly the same, and then you get also a resulting standard deviation. But because we have no standard deviation, we have to take an error from another source. And the concrete example is you have measured 2 centimeter plus minus 0.01 centimeter. Then we have the length B plus minus delta B, 3 centimeter plus minus 0.02 centimeter. And C plus minus delta C is 5 centimeter plus minus 0.02 centimeter. And what we are looking for is the average expected error for the volume. As I said, when that would be a standard deviation, we could also looking for the resulting standard deviation, but we have only a delta. And we would like to know the maximum possible error for the volume. That is the worst case scenario, when all 3 values have at the same time the biggest or shortest measurement, the biggest plus or the biggest minus error in this case. Here you can see it when all have the biggest, you have the biggest error. But when you have other mathematically connections, can it be that it is not so clear as in this formula? especially when you have things in like powered by a measurement value or divided by a measurement value, then can it be that you have local error maximas? And then it is a little bit more difficult to see this. So how works we? We have at first the average expected error. And you see the formula is A multiplied with B multiplied with C. And the exact differential is ABC derivated to A multiplied with delta A powered by 2 plus, that means here, this plus, ABC derivated to B multiplied with delta B. Then the formula ABC derivated to C multiplied with delta C. Every time powered by 2 and the root. And when you calculate the exact differential, you come to this formula, B multiplied with C multiplied with delta A powered by 2 plus A multiplied with C multiplied with delta B powered by 2 plus A B delta C powered by 2 and from all the root. So, and because we have everything in centimeter, I have saved here the centimeter. I have written only the numbers, but everything is in centimeter. And then you can calculate this and you get for delta of the volumina this number 0.2773 cubic centimeter. When you write here everywhere the units, the centimeter, it works also that you calculate the cubic centimeter. It must be in the end cubic centimeter. That is important. Also, especially when you have different units, when you have centimeter and millimeter, it is every time good to change the numbers to one unit, centimeter or millimeter, that every unit is the same unit, and you have, yeah, then it's easier to calculate. But it must also work that you get in the end cubic centimeter. So, and the whole result is now the volumina. Don't forget the volumina. You see here 2 multiplied with 3 multiplied with 5 is 30 cubic centimeter plus minus 0.2773 cubic centimeter. When you would have here a standard deviation, when the errors would be a standard deviation, then would be also this a standard deviation. And the calculation is exactly the same. You would have here a standard deviation, and then can you everything do what you can do with every standard deviation. You can double the standard deviation and can say in this range are 95% of the measurement values. You can make it 3 times and what else? Because the propagation of the standard deviation is mathematically absolutely clean. But when we have not a standard deviation, we take this other determined value, the delta of the delta of the error, and we calculate the average expected error. And here it is not working that you double this or so. That is, you know, not exactly how many percent are in this range. That can be 68, but it can also be more, especially when you have here an error class. An error class is every time bigger as a standard deviation. Then have you here also more values in the probability is higher as when you calculate with the standard deviation, but you don't know where this is. That is a question, but you can use it very good in the industry. It is the most used way. Also, if the mathematically connection is not really correct. So, and then we have had to calculate the absolute maximum error, the maximum expected error. And there I have explained we avoid the shortens by the sentence of Pythagoras. That means we power not by 2, we take not the root, so that we add the absolutely values. And you see, you have here the same principle. You calculate the exact differential. You derivate to ABC to A, ABC to B, ABC derivation to C, and then get you this formula. We put the values in, and the maximum expected error is 0.47 cubic centimeter. And the completely result is 3 cubic centimeter plus minus 0.47 cubic centimeter. The maximum expected error, of course, has to be bigger than the average expected error. You see here the average expected error. You see here the maximum expected error. For the maximum expected error, have you calculated the case that all 3 values have at the same time the biggest or the smallest value? The biggest or the smallest value in this case. That is the maximum expected error. But of course, the possibility is low that all 3 values have at the same time the maximum or minimum error, but it is the theoretically worst case that can theoretically happen. Have you questions? I know this part of the lecture is every time a little bit dry, but it is very important, and therefore we should make it. Later we have a lot of sensors that is more easier and not so dry. Okay, then I would like to show you a fourth formula, the error propagation for systematic errors, but I have written here it is mostly called as error propagation for systematic influences, because systematic errors we can correct. And therefore, in measurement and instrumentation, systematic errors, the propagation of systematic errors plays not a role as error propagation, but it must not be errors where you would like to calculate the resulting influence. When you have influences which are not errors, then can you calculate with this law the propagation of the different influences. And I would like to show you this on an example at strain gauges. Strain gauges are an extremely important measurement principle, especially in mechanical engineering applications. Many balances are working with strain gauges. Every time when you measure the mass over the strain, you can use the strain gauges. And the formula is also according to Gauss, but you must have here a concrete systematic error, +3 millimeter, for example, +3 millimeter, a concrete mathematically error. And so you see, when you know your error is +3 millimeter for applications in error, regarding errors, you would correct this. You would correct this and you would not calculate the propagation of this systematic error. But when this error is not an error, when this error is an influence, then it is important to calculate the resulting influence. And I would like to show you, oh no, I have skipped this. But I can show you on a, I have skipped this because that is too much, but I can show you this here. Strain gauges are, for example, metal strain gauges. That can be a wire, and you can have a body where you have here a strain gauge, here a strain gauge, and on the other side, here you have also a strain gauge, here you have a strain gauge. And when you, yeah, let me make it so. You have 2 strain gauges on top and 2 strain gauges here. And when you lead in a force here, then you have here a neutral line, and this strain gauge would be extended and this strain gauge would be compressed. And that means that this strain gauge would be a little bit longer, and the diameter would be smaller. And the resistance is the specific resistance multiplied with the length and divided by this area. But you see, the length would be longer, but the area must be smaller. And both leads to this, that the resistance will increase. That means here, when you have an extension, the resistance would increase, and on the underside, the resistance would decrease. And this can you measure? And the question is, when you have an extension by so and so much %, and you have a concrete calculation of how smaller this will be, then can you calculate, let me say here, you can calculate this delta of the resistance, what you get. But you must know the concrete influences. But that is known for strain gauges. And that is an example where you can use a systematic influence, the length, the delta of the length, a systematic influence to the propagation of the influence to the result. And for this, you can also use this law. But for error propagation, it has no, it is not important because a systematic error you should correct and not calculate the propagation. So, yeah, the example with the strain gauges I have skipped because it is a long calculation. And we come now to a next point, the evaluation and presentation of measurement results. Evaluation and presentation. In the past, it was so that we have had, in the most cases, not much measurement results. We have had every time too less measurement results for a statistical presentation. But today, it is turned completely. We have, in the most cases, too much measurement results, especially when you are in the field of electrical measurement systems. We have data acquisition cards which take 10 million samples per second. In 1 second, you have 10 million measurement results. And that can you not anymore print in a table. You have to compress the knowledge from this measurement results. And we have two cases. The first case is a measurement is carried out with the same equipment, with the same measurement devices, under the same conditions, and at not changing measurement target. That means everything is constant. And it will come to more or less different measurements, even when in an ideal way, all systematic errors are corrected. The reason are the random errors. In this case, when your measurement target is exactly every time the same and all the conditions are the same, then can you check your measurement system, because the errors comes from the environment, from your measurement system self, and therefore this case is to test the reliability of a measurement equipment, and you investigate your measurement system. But we have a second case where we use, let me say, principally, we use the same methods. And this case too, there you investigate changing measuring objects. That means your measuring objects, what you would like to measure, is changing. In the practice, we say that the device must be, the error of the device must be round about 10 times lower as the expected changing of the measurement measurement target, your things, what you would like to measure. I have an example here, a size analysis of 10,000 particles is statistically investigated, test of product quality. And this example comes from the industry. When you produce, for example, when you produce sandpaper, you have sandpaper, and the aim is that all particles on the sandpaper have the same size. It is glued on the paper, or partly also closes, but textile closes, but it is glued. And these particles should have the same size, because when you go over a surface, they take part all for the abrasive way, and it is very effective. But in practice, the analysis of this size would show that you have here the diameter of the particles and here how much particles that are, and that would be ideal. All particles have exactly the same size. That would be the aim. But in the practice, it is not true, because, for example, this is your particle size, what you would like to have, and then have you a little bit dust between. And the next particle has again exactly the size, and then have you again a little bit dust between. So that means when you make the analysis, that is a diameter, that is the number of the particles, then you have this diameter, what the aim is, but you have also particles between with another size. That means you have also smaller particles. What is the result? You have less points than here, and this paper would be not so effective like this, because you have less points for the abrasive function of the material of the sandpaper. And that means you have to move this paper much more up and down to get the same result like with this paper. But it is not dangerous. You can come to the same result in the end. It is only not so effective. But what is absolutely forbidden, when you have here your particles with the dust between, what is absolutely forbidden is a bigger particle. Because when this is a normal surface, what you would like to make more smoothly, then is that the scratch what you get in your surface. And therefore, when you have here your normal, it's not a normal distribution, but your normal function, and you have particles which are bigger, when you have a particle here to the bigger diameter, that is absolutely forbidden. And that must you test. And we have today devices where you can suck this material before you glue it on a paper. We suck it through a sensor. And for example, you have a photodiode, and the particles are going through this light beam on the photodiode, and you measure this impulse when a particle is crossing this area of the photodiode. There exist also other principles, Coulter principle, where you can really measure the volumina of this particle. Here you can measure only in 2D, but the Coulter principle can measure in 3D the particles, and these devices measure, for example, 10,000 particles in a minute, 2 minutes, so in this time range. And then have you to look how can we evaluate also this this measurement results. And for this, we look at first the evaluation and presentation of measurement results. We look at first for the standard deviation, because not the standard deviation, the normal distribution, because the normal distribution is the most distribution what we have when we have a measurement target. The normal distribution, and every distribution is describing by 2 parameters. One is a location parameter, and one is the uniformity parameter. The location parameter at the normal distribution is the expected value micro. That means here the micro. And the standard deviation is the uniformity parameter. How wide is this? How wide and how small is this deviation? The micro show where the distribution is. Where is he? On the Y as a measurement output signal, and the standard deviation say how wide or how small is it. And here is a very important point, that we have estimated values and we have true values. I have written here from micro and from the standard deviation. But I make it on this example with the micro. The expected value micro, we can never measure. What we can measure is a mean, but not the expected value. And that I would like to show you. When you have a measurement row and you have measured different values, then you can calculate the running mean. You take the first value, then you calculate the mean with the second value, then with the third value, with the fourth value, and so on. And what you calculate is going in a, let me say, in a tube, in a range, which is smaller and smaller, because the single value has more and more less influence when you have a high number of values. When you have 3 or 4 values, it's jumping from the mean is jumping very big. But when you have 1,000 values, then will be the 1,001st value change the mean not so much anymore. And when you let go this number to an infinite, then is this range 0 and you come to micro. That is the expected value of the mean. But when you stop your measurement row at the time point. And that is what we have to do in practical applications every time. Then can you calculate the mean? But the mean has a delta. The mean has a delta plus minus delta of the mean. This mean is, let me say, we try to get the micro, the true value. This is a true value. The micro has no plus minus, but you can never measure this micro. You can only estimate this micro by the mean with the rest of the error, but this error will be smaller and smaller when you have a higher number of measurement results. And so we can say, let me switch it back. So we can say the mean is the estimation of the true value micro. And this is with high probability, that's a mathematically expression close to micro. We can say if you have higher numbers of measurement values, then comes the mean closer and closer to the micro. And in the practice, we have to take the mean for the true value, because we can never measure the micro with an infinite number of measurements. And this is the same for the empirical standard deviation. We write the empirical standard deviation with S. This is an estimation of the standard deviation sigma. It is the same principle, because the standard deviation include also an calculation of a mean. You see, when I go in my drawing, when you calculate the standard deviation, so when you calculate the standard deviation, you say you have this changing values. You have this changing values, and the standard deviation, you compare the different to the mean. The different to the mean, and you have here the difference to the mean, but you would like to have a number which describe how strong is the scattering. When you have such a small scattering, the measurement rho is much more better. But when you would like to calculate the mean, you can get the same mean from this and this. That means the values with a sign with plus minus are not useful to calculate the standard deviation. And therefore, for the standard deviation, we calculate the mean minus the single value, the mean minus the single value, and we power by 2, so that all have a positive sign. All have a positive sign. And that means this would then be here. This would be here. And then we calculate the mean over these differences. We add from 1 to n, so much values we have, and we divide it by n, but not by n, we divide it by n minus 1, because the first value, what we have measured, say nothings. We have to divide by the comparisons to the first value. And the comparison to the first value is every time n minus 1. And that would be already the variance. And the mathematicians like the variance very much. And the variance is already a quality parameter for a measurement row. Because when the variance is bigger, then have you a more worst measurement row. When the variance is smaller, like here, then is it a better measurement row. But for measurement and instrumentation is a problem that the variance has the unit of your measurement value powered by 2. And you would like it not that you say, I have a length measurement and I say 10 centimeter plus minus 2 millimeter powered by 2. That makes not so really sense. And therefore, we take the root. We take the root and and then have we the standard deviation with the same unit as our measurement value. And you see that is the formula from the standard deviation. And you see we have here also a calculation of the mean in. Therefore, the standard deviation will go also in such a tube. And when you go with n against infinite, you get the standard deviation. If you cut it here, you get the empirical standard deviation. And the empirical standard deviation has a plus minus, depending from how many measurement values you have. Depending from how many measurement values. When you have less measurement values, you have a bigger delta of the empirical standard deviation. And when you have more and more values, you come closer to this true standard deviation for an infinite number of measurements. So, and yes, I think it is now 1:45. For today, I'm on the end of my lecture. And next week we start here. It is a little bit dry because it is statistics, but it is important and therefore should we make it also. But I can promise you we will have later the sensors and sensor systems. And when we have the sensors and sensor systems, then it will be not so dry. It's more very visible what we do then, and it is not so, also not so difficult. It will be better. I wish you a nice day.
Mr. Hoffmann?
Yes, yes.
I have one question.
Yes.
The schedule says that the next week we don't have a lecture. Is it true?
Yes, the next week is Mrs. Kukarenka has written to you an email, and she has written all the times when we have no lectures in the next time, because in we have next week is Easter, the whole week. Therefore, the whole week are no lectures next week. And we have some more holidays, especially in May. But look to your emails. Mrs. Kukarenka has written all the times where we have no lectures. Partly that are only single days, but the next week is a whole week completely free. Have you more questions? The next week would be interesting for you to travel a little bit. When you would like to travel also, we have, let me look. We have the whole week is free. The whole week, next week. And the Monday is also free. The following Monday, that is the 18th, because that is Easter Monday. That means we start then again with the lectures on the 19th of April. Tuesday, the 19th of April is then the first lecture day. But this week now is a normal week. Was it your question?
Yes, thank you.
Yeah, maybe you can go to the mountains. There have snow. There have still snow. We have had a couple of days ago a little bit snow. For some of you, I think it is a good experience to see snow, especially for the lady from Malaysia. But enjoy the week, the next week. Okay. Bye-bye.
Thanks, bye.
All right. Thank you.
Thank you, bye.